Hello everyone, my name is Diana and I'd like to present you our paper which is about capturing reality changes from point clouds for updating road geometric digital twins. My co-authors are Dr. Varun Kumar Reja, he is in the room. Yeah, please welcome him as well, and also Professor Ioannis Brilakis. So, so I would like today to talk about the critical issue of road maintenance and why relying on reactive maintenance is quite detrimental. As you can see from the slide, reactive maintenance, meaning that addressing issues as we've already occurred, is quite expensive. It leads to faster asset degradation, higher repair costs, and also imposes safety risks. On the other hand, proactive maintenance is the opposite. So basically, you deal with the issues before they become critical at the early stages or even in the preventive manner. And here we have lots of benefits like increased asset lifespan, increased safety, and minimized downtime. And unfortunately, in the situation when we don't have up-to-date information on our assets, achieving proactive maintenance is quite challenging. And one of the ways, as we see it, to go through it, to achieve it, is to use geometric digital twins, and which we talk about later on. And just let me give you an example why this situation is important. For example, if we consider the United Kingdom case, we can see that over the past 3 years, actually the average travel delay increased by 40%. And this is mainly due to road disruptions, the road work disruptions. We just close one lane here and there, or we close whole roads, and it takes a lot of time to repair that. Basically, this causes that we don't anymore rely on journey time estimations. It's always traffic jams there, and actually we now have in the UK slower average speeds. And yeah, so this may sound as inconvenience, but actually it is not. It has lots of economical impacts. For example, we just lose gross value added because of the travel delays, because like people commuting, instead of being productive, we spend a lot of time on the roads, for example. Yeah, so, and before we move on, let me just revisit the digital twin term. So basically, digital twin here we understand it as a digital replica of a physical asset, and it should be like a part of a twin system where you have a physical asset as a physical twin, and they have a bidirectional connection. So basically, we capture data on our physical twin. We scan them, for example, with LiDAR scanners, with images, with different sensors. We process that data, create our digital twin, so that we can run some algorithms on it, do predictive maintenance, for example, and initiate some actions on physical assets. And here we are going to talk about geometric digital twins, which are part of digital twins that focus on geometry of the objects, 3D shapes of them, along with relationships between them. So yeah, and in our work, we basically focus on creating an automatic method for updating those geometric digital twins. Basically, our method encompasses both detecting changes in the input point clouds and then applying those changes in GDT in one pipeline, so that you don't need to have any human intervention there. We covered here changes as additions, removals, so supposed changes like rotation, translation, and also deformations in a binary fashion. And we here understand like a geometric digital twin as a 3D meshed model. We assume they are in such format, but they could be a bit different, with all objects separately labeled, separately meshed. So yeah, as you might guess already, our approach is a two-layer approach with change detection and change application layers, which we are going now to cover in more details. So we start with the input. We have 2 point clouds, older version and newer version. So the older version of the point cloud might be the original point cloud that was used to construct initially the geometric digital twin. But in the case if it is not stored, if it is too heavy to store it, we can subsample a point cloud from 3D model. And then when we have both of them, a newly scanned point cloud and older one, we compare them on the point-to-point basis. Basically, we compute distances between points between these 2 point clouds, and our task is to find high change regions. We do that by using thresholding. As we find with high change regions, we assume, okay, like changes that belong to one object, they should be close to each other, so that's why we use clustering with the base scan here. And then when we have that, we need to match them with each other. So basically, for matching algorithm here is quite simple. It is based on the assumptions that objects that has changed, they should be close by to the original location. And yeah, after doing that, we detect type of changes. So basically, when we have matched clusters, we estimate transformation there using iterative closest point algorithm, ICP. And if there is no match, we assume it is addition or removal, depending on the order of point cloud. And if there is no pose change, but still something has changed in that region, we assume it is some sort of deformation. So basically, we can replace the object in the GDT. And yeah, as a result, we apply those changes. We can change the current objects in the geometric digital twin by applying like rotation, translation changes, for example, or we can create a new timestamps objects. So basically, we can view then changes from the time in the geometric digital twin. Yeah, and let's now look a bit on the examples and the results. On the top row, you can see 2 input point clouds. And we created our own synthetic data set with simulated changes for this because in the current, unfortunately now public data sets are not available for those environments. And on the top row, you can see like we, just for visualization purposes, we covered with input point clouds in red and green so that changes are all visible. And on the second row, you can see found changed clusters that were already clustered. So our next task was to match, as you might remember them. And if we look at the results of matching, we can see that we have pretty good precision, but recall is quite lower. So this is the future work direction. And one of the I would just want to mention several reasons why it might happen. So one of the reasons is that sometimes it becomes an ill-posed problem. For example, just imagine a typical highway and you have lots of standardized objects there, like for example a lamp would be like lamps would be super similar to each other, and if some lamp has changed and a similar lamp has been added, so using point clouds, basically, sometimes it becomes impossible because they look absolutely similar. So in such scenarios, we consider for future work, for example, using images because they provide high quality input, and there we can see some signs of aging, for example, little deformations like scratches, so we can identify, okay, this is a new lamp and this is the one that has changed. Yeah, so, and also in the future, we plan to improve our matching algorithm to make it more sophisticated. Yeah, so that is about results, and in the conclusions, I'd like to say that we developed an automatic method that serves as a proof of concept for updating such geometric digital twins. So it brings us basically one step forward to industry adoption of digital twins. Yeah, and as a result, we can improve productivity there. by reducing manual work, reduced travel time, so basically everyone benefits from them. Yeah, so I already mentioned our future work, some of our future works like integration of images, and we also want to improve matching and also estimation of transformations. Thank you so much for your attention, and here's my LinkedIn. Please find me there. Yeah, thank you.